two remaining topics in potentiometry, and it is a thing. Yeah. Actually, there is a technique. If it's in our book, it's not in this part of the book. It's probably in the back part of the book, which is where the instrumental stuff kicks in.
Oh, yeah.
It's a separate class. There's something called cyclic voltammetry that measures this. It's called a hysteresis loop. They're really unusual to look at. Most people without a trained eye don't know how to read them. Where you make a redox reaction happen backwards and forwards by cycling through the potentials. Yeah, kind of useful in biochemistry, where we know that lots of redox processes exist. It's outside the scope of what we're doing, because it really relies on, it's computerized. So it becomes instrumental, not quantitative.
When are you teaching instrumental again?
Next spring. There's a thing called formal potential. Formal potential is a conditional value. Everything that we've seen up to this point, we've allowed a concentration to be in. Hot on the heels of saying concentration isn't allowed because everything's supposed to be an activity. And if you look outside of our textbook, everything that's written is written the way that we've done it on the board. A couple of changes here and there and some of the notation. Our book always writes activities and then says, assuming activity is 1, just go ahead and switch it for the concentration. It always has leaned in to the fact that activities are the numbers, okay? Well, here's where it kicks in. If H plus acid is involved in your reaction, then you get an activity for H plus that is equal to 1 only when pH is 0, which is unreasonable. Yeah. pH could be 0.
Well, I understand that, but if it's involved in the reaction.
If you've got an H plus in your equation, therefore it has to be accounted for. Then the activity of H plus happens when the concentration of H plus is sufficiently high to give you a pH of 0.
So that's the highest pH you can get?
Yeah, well, yes.
Dr. McGuire.
When you say high, you mean low.
Sorry,
Yes.
when you have the
Yeah.
highest amount of H plus in your solution, you get a low.
There are things called superacids that have negative values of pH. Yeah.
How does that?
We try not to let the first and second year undergraduates know this because It's the same thing as telling them, hey, you know, concentration doesn't exist. Pressure doesn't exist. You need fugacity. You need activity. Everything is a lie. Okay.
Essentially.
Yeah. So this right here. We have a pH scale from 0 to 14. The 0 to 7s are the acidic part. The smaller the number, the more acidic. The higher the number, the more basic. And this is unreasonable in most cases. That's just too high a concentration of acid. It's unreasonable. The outcome here is that reduction potentials are pH sensitive. Don't know if I want to say the word sensitive or dependent. Dependent will work. Okay. Now there's a thing called the standard hydrogen electrode. And the standard hydrogen electrode is a very sensitive piece of equipment. It's a little bit cumbersome to use, but it's what we set our value of hydrogen to be 0 for the reduction potentials. Okay. We're going to invent, and I say we, it's not really chemists doing this. This is mostly biochemists, because biochemists will work under situations where you say, hey, blood plasma, pH is 7.4, stomach acid, pH of 2.1 or whatever. And they'll set a pH that is biologically relevant for the reaction to happen. And because reduction potentials are dependent on the acid, because the acid is part of the reaction, and it's unreasonable to say, I'm going to look at this little delicate equilibrium, biological equilibrium, that happens at pH 7.4, and then have the math underpinning it, have my pH be at 0. Okay. I'm going to invent a new one. Here's our reduction potential. That's our standard reduction potential. I'm going to give it a apostrophe, or yeah. Sometimes, mostly it's just a little prime or an apostrophe. Occasionally, it gets to be this. If you were to magnify that, it's a little tiny wedge with a line that goes here. It's the symbol that we use for transition states in reaction chemistry, that something passes through. And sometimes it's got 2 bars in it. This will do. This is going to be called our formal reduction potential. And what that is, your standard reduction potential measured against the standard hydrogen electrode. So when I said there are two things left in the chapter, one is this, and all I'm going to do is tell you that it exists. I don't think that we're going to chase down any examples. And the other thing are the specific electrodes. We brought some to class on Thursday. They look unassuming. The standard hydrogen electrode is a piece of glassware because it uses actual hydrogen gas. So it's kind of a double-sleeved piece of glassware that has actual hydrogen in it. And then platinum electrodes just look like pieces of wire. They're pretty unassuming. So that part for the specific electrodes, when you would use this electrode versus that electrode, I'm not going to bother teaching that. There's an entire chapter in the book about it. That's going to be a homework assignment of compare and contrast uses and capabilities of any two. Pick any two. The common ones out there: calomel, which is a mercury chloride, platinum, glass, standard hydrogen, and then you've got the ion selective ones as well. All right. So the only time that we would need this is when our conditions are really a long way away from having an activity of 1. When we're a long way away from it, so biological conditions. Okay. So the E, the formal standard reduction potential. Oh, I've missed a standard. I don't know if you have to say formal and standard. Probably, because the standard is in there to tell us conditions. The formal standard reduction potential is the regular standard reduction potential. And then here's our modifier. Negative RT over NF with the natural log of gamma reduced over gamma oxidized. What's gamma?
That is the activity coefficient.
The activity coefficient. And what's an activity coefficient?
Does it tell you how much your concentration deviates from the?
It's the thing that you multiply concentration by to get activity. So it's the modifier that says you are off by, you're adrift by this much. Okay? All right. Well, with a little bit of creative math, you can move this around so that your reduction potential is your standard, your formal reduction potential minus RTNF, natural log concentration of the reduced species over the oxidized species. This now is what you actually measure. Okay. And our book has I've moved on to a different chapter, but if I go back and find it, what were we in, 19? Something like that? They have a table of here are all formal values. I've never used it. That doesn't mean that it doesn't get used. It means I've not done sufficient biochemical electrochemistry. I've only done the regular general chemistry stuff. Okay?
Dr. McGuire,
That's it.
I think you already said it, but how did, so whenever you're no longer doing standard, why can you now make that concentration instead of the activity coefficients?
We don't know.
Oh.
It's somewhere, so what we'll have done is there's whatever the math underpinning this is has been rewritten a couple of times to give that one out. I didn't chase it down because I wasn't invested.
Okay, I'm just trying to make sure I wasn't.
No. No. Our book doesn't always show you what the steps in between are, but it's a tiny bit better than the book that preceded it. We used to use a book that's very famous. It's in wide use. And instead of skipping 1 or 2 steps in the math proofs, they would skip like 7.
Wow.
And so it went from, here's a giant jumble of numbers and terms down to A equals B times C. And the students would just cry because
I'm just joking on water, it's fine.
they couldn't figure it out. And we would spend time just trying to decipher the proof, the mathematical proof of why do these numbers mean the same things, which we know from physical chemistry has destroyed the subject. That they spend all the time proving that this equation is equivalent to that equation without ever using the equation to find anything useful. It's a complete waste of our time. Okay, so just letting you know that it exists. It's there. I have no plans to use it. And I will set you a piece of coursework for the forced reading for the ion selective electrodes. Okay? And then I figured, what could we do that would be really quick and useful, but isn't really in the book? It's half a page in the book. And will just stand on its own, and that's refractive index. Do we know what refractive index is?
Remember we used the thing to gauge it.
Did we actually, what did we use that for? It's called a refractometer.
Well, I know we put syrup on it, and then we put something else on it. We were just trying to measure, I guess, the refractive index.
I think we were just trying to make sure that it worked.
I think so.
Oh, Ashley was there, right?
She was there.
What was Ashley doing? I can't remember. Yeah, so we have a couple, and I brought them, and we'll talk about them when we need to. I also brought paper towels because we're going to make a mess.
Yes, we are.
Yeah. Okay. C is the speed of light. What is the speed of light?
2 something.
Times 10 to the sum or other.
10 to the, what is it, 19? No, 23?
Oh, we don't want that with that.
Equals.
It's about 300 million meters per second.
Dr. McGuire, I think we were trying to see how not to overshoot it, because we put like too much syrup or something, and then it just went over the whole thing. So I think we were trying to learn how much
Oh, I know what she was. I remember. I know what she was doing.
What was she doing?
She was measuring phase diagrams.
She was.
Do you remember we were
with the
doing phase
triangle.
triangle? Yeah. Which you will do after the break. We'll do that after Easter. Because Ashley wrote it, so you are going to prove it, and then we're going to implement it. You're going to be guinea pigs. It's good. It's an interesting thing.
We get Easter break
Yeah,
2 days.
Thursday and Friday.
next week.
This week.
Oh.
Good Friday is already here. This Easter season is just gone really, really quickly. Are we sure?
Well,
Okay.
I'm not sure.
Are there any conditions with this?
It's an intensive property.
No.
It isn't.
It is not.
It isn't. I don't know if I can blame Newton for this one, and when I say blame, I don't mean blame, I mean the credit. Light is a fixed quantity. It's unchanging, and you can never change it, and it's always going, which is not true.
Is that the
And outside of what Einstein says of if you travel relativity, it's not true. This is dependent on medium. This is the speed of light in a vacuum. When light passes through a medium, then mu is the speed, not mu is the speed of light, and it is equal to c, which is the speed of light in a vacuum, divided by n.
Not N again. What does it stand for this time?
Refractive index.
Wow.
why do you do
This is annoying. I don't like
He
having
laughs.
5 N's
He
in the same
laughs.
class.
Yeah, I'm not happy with our book deciding to go capital N versus lowercase n around Nernst equation. So this is again a modifier that the speed of light when it travels through some medium is, I'm going to use a science word, retarded, which means slowed down. Okay, it's all that means. Well, we're not allowed to use that word in common usage anymore, but it is actually a thing. You know RF in chromatography, the retention factor? It's not retention factor, it's retardation. That's how it was written, that's what it was meant, because it tells you as the things are moving across the solid medium, some of them are slowed down more than others.
and then they ruined it with what they did.
Well, I'm not going to say it's ruined, it's just changed. But the whole evolution of language means when you take a particular word away because that's now deemed offensive, it just moves somewhere else. I was teaching a bunch of kids, you know, I coach on a Saturday morning, and they said something along the lines of, they asked where a person was, and I said, they're over there. And they all fell around laughing, because I had said they.
Yeah. Really?
So, see what you've done?
Yeah.
You've decided that society needed to be more cautious with the particular word, and now adjust words. Okay, so this depends on the medium. Here's how it works. And we've all seen this. Here's a pool of water. And here's a stick. It's a man with a stick. What do you say when you see a man with a stick?
A man with a stick.
We're getting really esoteric English humor. There's a saying of what you say when you see a man with a stick. What's on the end of the stick, baby? I'll have to show it to you. I'll have to bring up the video. Anyway, when the man with the stick puts the stick in the water, it appears to bend, right? We've all seen that.
Yes.
Okay. Does it really bend?
No.
No. How do we know it isn't really bend?
We take it back out.
Because when you take it back out, it's not bent.
Yes.
So, we have an interface. This line right here is the interface between two media, or mediums. Sometimes words are allowed two different plurals, depending on how you use them. It's like syllabi and syllabuses. That one's gone away now. It used to be that if they were different types, they would be syllabi, but if it was multiple copies of the same type, they would be syllabuses. Or the other way around.
I feel like it should be medium.
Or the other way around. Who knows? This is medium number 1, and that is medium number 2. Medium number 1 has a refractive index, N1. Medium number 2 has a refractive index, N2. The light travels and impinges at the interface at a particular angle. We measure that angle by inventing an imaginary line that is perpendicular to the interface. A line that is perpendicular to another line is called a
Right angle.
that goes along with the perpendicular part.
A line that is perpendicular to another line is. Oh.
That's a normal. Okay. So I have a right angle to the interface. The incident angle is going to be called theta 1. And the exit angle is called theta 2. And Snell's law says,
This is from physics too, right?
I don't know where, wherever optics is.
Physics too.
We haven't got there yet.
You haven't done physics?
Well, I'm doing physics 2 right now.
They haven't gotten to this part.
We just took a test over generators, motors, magnetic fields, AC circuits.
Is it like N1 sine theta?
Absolutely is.
Wait, what?
why we love trigonometry. Sines work. Okay. Now, how could this possibly be of use to us?
Well, if we know N1 and theta 1, and then we figure out, oh, theta 2 is this, we can find the median of the other.
Depends on the median, right?
Mm-hmm.
Oh, hold on. Just thought of something. I'm going to go all 20th century on you.
Perfect.
I'm gonna go all 20th century. I hope we come back soon.
Oh my gosh, I'm so tired, guys.
At least the sun's out today.
That is true.
Do we want to try independence day?
No, I don't want to.
Oh.
This is called the Rubber Book. It's a book that was published every single year by the CRC Rubber Company, and it's called the Handbook. Handbook.
Oh, yeah, handbook.
Yeah. And the pages are really thin, very, very thin. So this is the internet.
Yes.
This is what the internet looked like in 1970. 1988.
Really?
Still before the internet. Still before the graphical index interface for the internet. And somewhere in here, there is page after page after page after page of refractive indices. Here we go. Okay. This is only for organic chemicals, the part that I'm going to show you. This many pages. It is every named organic chemical that you can possibly think of. And it tells you formula mass. It tells you whether it's a liquid, a solid, and if it is a solid, what type of crystalline form it is. It tells you its boiling point and melting point, its density is the characteristic value, and then the next column over, refractive index. And the refractive index of ethane sulfonyl chloride is 1.4531, but ethane sulfonyl chloride 2-bromo is 15242. Somebody's put in a huge amount of work. So all of those values are known and recorded and tabulated for hundreds of thousands of chemicals. And now we just have the internet. Okay, a couple of things about N. N has no units. It is usually measured relative to what we call the D line in the sodium emission spectrum. Do you remember that part where we brought the emission lights out and you looked through the diffraction gratings and we saw the emission spectrum that was quantized, and then we went ahead and found the individual frequencies or wavelengths of the light for it? Well, the lines are labeled A, B, C, D, E, F, G, and sodium has a very, very strong D line, 2.8, what is it? I wrote it down. 589, which is 589.3 nanometers, and we measured that at 20 degrees Celsius. 20 degrees Celsius is not a standard number. 25 would be, but everything's already been recorded, and no one's going to go back and record them all again. Okay. So this is called now N20D, or sometimes ND. Mostly this one, or ND20. I've seen it written that way. This is what we normally see, ND20. Actually, 20D is the wrong way around. ND20 is probably right. Okay. Let's look at a couple of values. Obviously, these can be tabulated and have been tabulated. If you're a vacuum, you have an ND of unity. Air has a value that is 1.000293. If it's a gas, we measure gases at STP. Standard temperatures and pressures. What's the standard temperature for gas recordings?
298 Kelvin.
No, it's 0.
Oh, right.
Standards are all over the place. The standards for gases, standard temperature for a gas is 0 degrees Celsius and 1 atmosphere, which is 101,300 whatever it is pascals. 1 atmosphere. Now, when you're a liquid, we switch to being at 20 degrees Celsius. Olive oil, something like, this is dependent. There's going to be a lot of variation there because no two olive oils are the same. It's a natural product. And some olive oil is tinged green and some of it is much more colorless. It's why they put it in, when people are taste testing olive oil, they put them in blue bottles So you can't tell what color the oil is, so that the subconscious bias of the taster will say, well, I only like the green colored olive oil. So this is going to really vary. As is this next one, because glass from two different factories is going to have different refractive indices. Actually, I'm going to make that be a 2. And then diamond, very high refractive index. Bends light, traps the light inside the crystal, bounces around, and makes it look pretty. And then, of course, there's honey. And honey has a refractive index between 1.3 and 1.7. This is a refractometer. It has an eyepiece that twists. You ever use binoculars or a telescope? And you have a little focal element right here that's going to help you look through it. And then there is a sample holder, and we're going to put our sample on there and then slap that over, and then physically look through. I'm not sure I'll ever be able to get this on camera, but if you hold it up to the light and look through the viewfinder, you'll see a little scale. It's a bit out of focus. Well, for me it is. And this one on the left says refractive index ND. And this one runs from 1.5 to 1.44. So a narrow range, which probably tells us that this is used in the food industry. That this is looking for something like that will always be in that range. Okay? If our honey is in that range, then we'll be able to see it.
What if it's not?
Then we'll use the other one. Two. And one of them might work, both of them might work, neither of them might work. This next one, so I have this lovely 19, there's 2 color, so it could be from the 1980s, could be from the 1990s, catalog. And one of these hand refractometers is for honey. One of them is for like oil slicks. One of them is for vegetable oil. And one of them in the food, oh look, it tells you what the uses of each particular instrument are. You're looking at orange juice, you're looking at, so they're used in the food industry.
And how does that, I guess, how would they use that information in there? How would they use that, like, cause it's like, oh, cool, it has refractiveness of this.
Yeah.
How does that apply to, like, I know it's probably different for everything, but how does that apply to the
So,
job?
the refractive index for, let's pick out the one that we're really interested in, honey. The refractive index of honey depends on the sugar to water ratio. And the sugar to water ratio, this is a separate one, look through that. In the food industry, these are all NDs. or ND20s. The food industry uses something called the BRICS unit, which is percent sugar to water. So 10 grams of sucrose in 90 grams of water is 10% BRICS. Honey has, from what I can remember, like 80 BRICS. It should be something like 8 sugars to every 2 waters. The fact that it has so little water in it is one of the reasons that it doesn't degrade. That we know that bacteria love sugar and water. And that if we cut open like an orange or a grape, that sugary water is going to be attacked by bacteria immediately, and it will start to rot and ferment. But honey doesn't. Honey doesn't, because its water content is too low for the bacteria to grow. If you took some honey and you watered it down, it would start to rot pretty quickly. Okay? So, we have some honey, we have some paper towels, we have 2 refractometers. Go tell me what the refractive index of them are. And I'm not sure that our ND one will measure, because we might be off, but the BRICS one should. I think it will. What were when you read the BRICS, what was the high? Because honey does have a very high BRICS count.
32 to 0.
Oh, then no, it's not going to work. It's not going to work. So when you look through the viewfinder, you adjust the focal length, and you get to see this. When you slap a sample on the sample holder, it puts a meniscus somewhere here that this is now a different tone, it's a different color, and you get to see the line, and then you read off what that is. Okay, so we do need to know what the refractive index of our honeys are. So let's see if we can see it. One of them will be off scale, one of them hopefully will be on scale.
So use both anyways?
Yeah.
I would start with like a dab, like a squirt. Yeah, like that.
It's now like wine, like you remember how dark it was before?
Yeah, it's
Now it's all
very
light.
That's cool. Yeah. It fills up.
There's nothing like,
It
there
fills
was
up the
no,
whole thing because it overshoots it.
there was no like tonal difference except
Yeah.
for the slider. Originally it was like a, like. you
So
know,
these cost about, these are going out of fashion. I looked up the manufacturer of one of these, and they which for an instrument is not bad at all. I just buy one. Yeah, so we're off scale.
When we wipe it, Dr. Warren, do you want us to use Chem wipes or
Yes. Yeah.
Chem wipes?
Yeah. I really brought the brown paper towel because I figured that we would be making a mess.
Oh, okay.
Did you see anything?
Mm-hmm.
What'd you get?
1.49.
Ah. There you go.
Oh, yeah. That's good.
That one went off scale.
1.49. 7.
Oh, look at that. It's really beautiful, isn't it? It's
Yeah.
blue and white and it's very, very sharp.
Yes.
1.4956. Not quite to the 7. So, like, you could even throw a third decimal in
Oh,
there.
yeah. That's what I was
Of 1.4969. Okay, let me see if our camera can see that. I doubt it, but you never know. No, we've got to get it all the way through. I don't think that's ever gonna. Okay, write that down. Read that number.
Oh, I'm sorry, 1.497.
It's a tiny bit under 7. You could even throw in, yeah, you could even guess at what the next one.
It's
When
under
it's-
7?
Yeah, I think it's a tiny bit under. But that's very, very clear,
Yeah.
right?
It's very precise.
That's for the HB honey,
Okay.
and that is a number that you need to write down.
Okay.
And we'll go and test the other 2 honeys. We'll do that. Okay?
Do you want me to go down? The left?
We'll head that way.
Okay.
Okay. What's in your immediate future? Piece of homework about the selective electrodes. A week or 2. And you have an exam coming
When?
because we're done with potentiometry. I've got an exam to write for chemistry 2 today, and I will write yours today or tomorrow. And then post it. It'll be the same as the last one. Of.
Those are only in person.
No. No.
Dr. Warren.
No. We get to write big questions, better questions when you have more time to answer them.